Physics chapter 17, video 10 theory. Now we are going to look at the origins of centripetal forces. Now, in earlier situations, earlier examples that we discussed, the centripetal force was quite obvious. But sometimes it might not be that obvious. We might have some difficulty figuring out what exactly is going to give the centripetal force. However, when trying to figure out what is going to give the centripetal force, what is going to provide the centripetal force, one thing that we need to understand is that always these forces are not balanced. That is the reason why there is a centripetal force. So this centripetal force is going to be a resultant force. That is, it is unbalanced force. That means, in simple terms, there has to be, a kind of a situation where one force, the opposing forces, have exceeded the other forces that are acting against it. So in this situation, a resultant force is generated, and this resultant force is going to make the object move in a circular pathway. So as a result, you have to understand that if an object is moving along a circular path, it is not in equilibrium. And that resultant force, which is going to break the equilibrium, is going to provide the centripetal force. Now, let's look at this first example that they have given. A car cornering on a level road, right? A car cornering on a level road. Here, the road provides two forces. The force N is the normal contact force which opposes the weight, because if the weight and the opposing force N, if they are not balanced, then the car is going to sink into the road. But it doesn't happen. So it is naturally there on the ground. So the weight has been cancelled out by the force N, or the reaction force. So that is the reaction force is against the weight mg of the car. So there is no acceleration in the vertical direction. There is no upward or downward movement. Right? So now here the figure, if you look at the figure, they have given an explanation. This car is moving away from us and turning to the left. Friction provides the centripetal force. N and F are the normal contact forces, and the normal contact and frictional forces. F is the frictional force. N and mg are balanced out. Right? So the force is contact with the road by the tires. Right? The four tires are in contact with the road. So they are going to provide the frictional force. The second force is the force of friction F between the tires and the road surface. That is the unbalanced centripetal force. Right? If the road or the tires cannot provide the friction, then car cannot go around the bend. That is, if it is raining or if it is oily, then it might skid off, or skidding means it is going in a straight direction. It is not turning the way it should be. It is not able to provide that centripetal force required. Right? Then the second one, the car cornering on a banked road. Banked means it's slanted. Right? If you look at the diagram, you will understand. Then the normal contact force N, right, has a horizontal component which can provide the centripetal force. The vertical component of N balances the car's weight. Right? The vertical component of N balances the car's weight. Therefore, vertically, N cos theta is going to be equal to mg. Horizontally, you are going to have N sin theta, which is going to be equal to mb squared upon r, which is going to provide the acceleration. Right? So I hope you understood that. This theta story, you have to, you can use your mathematical knowledge to figure out that part. If you find it difficult, please do ask me questions. You can raise questions, and If you have difficulties, you can raise them. Then so in this particular situation, r is the radius of the circular corner and v is the car speed, obviously. Now what would happen is, now if you have gone to these different events that they hold, and there are these death wells where they ride motorbikes or cars on walls of a circular well. How they do it is because they are actually going really fast. When they go really fast, that wall provides that slanting, that the wall provides the centripetal force needed for this object to go in a circular pathway. But if he slows down or if he brakes, what will happen? He will fall onto the ground. Here they have explained it. If a car travels around the bend too slowly, it will tend to slide down the slope, and friction will act up the slope to keep it on course. If it travels too fast, it will tend to slide up the slope. If the friction is insufficient, it will move up the slope and come off the road. So once again, you have to understand why it is important to have these values of these forces balanced. They have to be in the proper values to make sure that there are no accidents taking place. Then an aircraft, when it changes direction, it banks. Banks means it kind of slants itself, as shown here. So usually a plane would travel in a kind of in a straight line, right? So let's say this is a plane, it goes, but if it is going to take a bend, it will go like this. It will bend if it is turning in this direction. If it is turning in this direction, it will turn this way around, right? So that is how it happens. You can actually see this in when people on bikes, when they take bends, they do that. They bank it. An aircraft banking, figure 17.15, as you can see it here, that banking provides the centripetal force. To change direction, the pilot tips the aircraft's wings. The vertical component of the lift force, L of the wings, balance the weight. The horizontal component of L provides the centripetal force. Right? If not, there is nothing to push it sideways. It cannot, if it does not bend, it cannot go around that corner. It has to bend, right? It has to bend. Then fourth one, a stone being whirled in a horizontal circle on the end of a string. This arrangement is known as conical pendulum. The vertical component of the tension T is equal to the weight of the stone. So this is a conical pendulum. You don't rotate it horizontally, but there is a vertical component. The vertical component of the tension T is equal to the weight of the stone. Right? So this T is going to be equal to the weight of the stone. Horizontal component of the tension provides the centripetal force for the circular motion. So the horizontal component will provide just like here, just like in this car situation, it will provide the centripetal force necessary. At the fairground, as the cylinder spins, the flow drops away. This is not quite common in Sri Lanka though. In fairs, they have these cylindrical spins where you go and lean against the wall. When you lean against the wall, it starts to spin really fast, and the flow drops away, and you start to rise up against the wall. You will feel as you are being pushed against the wall. But what is truly happening is you are being pushed front towards the center by the wall. That is the way it provides the centripetal force. Always remember, the force is towards the center. Now here, the three more ways of providing centripetal force, that's what we explained. Note that the three situations shown in figure 17.14a, figure 17.14a and figure 1.71.15 are equivalent. 17.15b are equivalent. The moving object's weights act downwards. The second force has a vertical component which balances the weight, and a horizontal component which provides the centripetal force. So this T has a vertical and a horizontal component each, and the vertical component balances the weight, and the horizontal component provides the centripetal force. Right? So let's write down a note on this. Write down the origins of centripetal forces. Sometimes the centripetal force may not be as obvious as above situations. In below situations, the centripetal force is provided by a component of its weight, a component of its weight, a component of its weight, or friction provided by the surface in contact. Number one, when a car takes a turn in a level road, the weight of the car is balanced by the reaction force. The weight of the car is balanced by the reaction force as shown below. And the friction between the ground and the tires, provide the centripetal force necessary. Please draw a sketch of this figure 17.13. Then number 2, when a car car cornering on a bank road, within brackets write slanted road. The normal contact force N has a horizontal and a vertical component. Vertical component will balance out the weight of the car. While the horizontal component provides the centripetal force. Please draw these diagrams, then you would understand it better. And then write. You will have to write down these vertical and horizontal components. That is these equations. You will have to write them as well, and then draw the diagrams, and then leave a line and write down. When an aircraft changes direction or turns, it will follow the same procedure. The lift force on wings and its horizontal component will provide the centripetal force. A conical pendulum and also a spinning cylinder, beg your pardon, a conical pendulum will also act the same way as the plane as well as the car on a bank road. But a spinning cylinder the friction against the wall provides the centripetal force. Right. I hope you understood this part. Please do question number 19, 20 and 21. We will discuss them and then we have to move into the end of chapters. Before you move into the end of chapters, please make sure that you make a kind of a short note to remember all the equations. So you have to understand what omega is and the equations A equals V squared upon R and R omega squared, then the other equations, all of those equations need to be there. So make a kind of a small, very, very small short note. I'm not telling you to write the theories, but I'm telling you to write the equations so you know which equations are to use. So first, please do 19, 20, 21 and go through the summary as well, and then start doing the end of chapter questions. In my next videos, I will be discussing the end of chapter questions as well as the last 3 questions. Thank you.